Hello everyone, in this video we're going to go over some practice problems for Chapter 6. I recently created a SAS Basics tutorial that goes over how to import some data and some commonly used functions that are heavily used throughout this video. So if you haven't already, check that video out. It'll really help with this one. And with that said, we can actually go ahead and get started. So for our first example, we have random samples from 11 male high school students and 12 female high school students, and they participated in a public health awareness test, and we're trying to investigate if there's a difference between test scores between the male and female participants. If you recall from the SAS Basics tutorial, we're going to start off by importing our data. We're going to use the data function along with the name example_6 _6, and then end that off with a semicolon. Our next line is to input our two variables, gender and test. The $sign is to indicate that gender is a non-numeric variable. Our next line is going to be data lines because we're going to be pasting our data like here. And then we can actually highlight and run this entire block of code to make sure that everything is importing correctly. So if we go ahead and hit run, we can see that we have both variables accurately entered, and we can go ahead and start the next line. And then we're going to run a proc means command to get a basic summary of our data, so we can go ahead and run that. So as we can see, we have 23 observations, so that signifies that we have successfully imported our data. So if we wanted a bit more specified statistics, we can actually run a means command, but break the statistics out by variable. So we're going to use var test and class gender options to do so. This allows us to break out the statistics created by the means command by the categories defined by the gender variable. So just looking at the summary statistics in the output here, so just a brief observation is that the calculated statistics look very similar. The mean values don't seem too far off between the two groups, and the standard deviations look relatively similar as well. If you recall from the SAS Basics tutorial, you can use proc univariate to find very similar summary statistics to proc means. So an alternative to the proc means function, we can use that proc univariate with the plots option, as well as var test and class gender. This will result in an output that has very similar statistics or descriptive statistics to the proc means function. This time it's divided into two sections. So this first section is going to be for gender female, where you can see a lot of the same metrics as the first proc means function. However, the benefit to the univariate function as opposed to the means function is that option for plots. So here you can see the histogram of the distribution for the female population as well as the QQ plot. And the same exists for the male. So we have the same statistics or very similar statistics as the proc means with more information obviously. And then again, we have that histogram and QQ plot featured down here below. And then a brief observation, we saw it with the female plot, but this QQ plot for the male population looks relatively normal. All the residuals seem to be plotted fairly linearly on that QQ plot. And since the data look normal according to the QQ plots, we can actually go ahead and test to see if the variances between the two groups appear to be equal. So we can run a proc box plots command and plot test and gender and compare the box plots to see if the variance between the two groups might be or appear to be equal. Unfortunately, from the box plots, it's actually kind of hard to tell whether the variance between the two groups are equal or not. The interquartile range for the female group seems to be a bit shorter than the male group, and formal testing like a Levin's test might be necessary. So luckily, in SAS, when we perform the t-test function, there actually exists an output where it performs the test for homogeneity for us. So if we go ahead and use proc t-test along with our data with the variable test, and class gender, we can run this command here. And the resulting output, it's going to be a couple of tables here up above, but if we scroll down, we can see some of the checks for the assumptions made for using a two-sample independent t-test. So this first plot here plots the distribution of the two samples, and both look pretty normal. And then further down are the QQ plots, and here the residuals follow that linear line really well, so there's no reason to believe that the data we have is not normally distributed. So now that we checked to see if the assumption of normality holds true, we can check to see if the variances between the two groups are equal. So that fourth table there is the folded f-test. And with the folded f-test, we assume that the null hypothesis is that the variances are equal, and the alternative being that they are not equal. And so since we have a p-value well above our level of significance, we don't have enough evidence to support rejecting the null hypothesis, and therefore we can conclude that the variances between the two groups are in fact equal. So since the variances are assumed to be equal and the data is normally distributed, we can go ahead and use a pooled two-sample t-test. So since we're trying to differentiate whether the two groups differ in mean, our null hypothesis for the two-sample t-test would be that the mean for group 1 and 2 are the same, or that they equal 0, and our alternative hypothesis is that the difference between the two groups does not equal 0. With that being said, we can look at the third table here, and since we assumed that our variances were equal, we can look at that first line of the third table. All the way to the right, we can see that we have a p-value of 0.91. This indicates that there is not enough evidence to reject the null hypothesis. Therefore, we can conclude that there is no statistically significant difference between males and females for the test scores. And in determining that there was no difference, we've answered our question of interest, so we can actually go ahead and jump to question 2. All right, for our second example, we have a nutritionist, and they're trying to determine the effectiveness of a weight loss program. So we have 10 subjects that were weighed before the program and then after the 6-week program, and we're trying to determine whether there's a statistically significant difference between the starting weight and the final weight. Like our first example, we're going to start off by importing the data. So we're going to start off by using the data function and calling it example_6_10. We're going to input the two variables initial and final. Then we're going to create a new variable called diff, which is the difference between the initial and final. We're going to call the data lines function because our next lines are going to be our data. Once we have the run command, we can go ahead and highlight that and make sure that everything is importing correctly. Looks like all 3 fields are good, so we can go ahead and head back to our code. So with the paired t-test, we can actually jump right ahead to use the proc means function. We can call our data using the data equals option. Then we can use options n, mean, std for standard deviation, stdir for standard error, t for the t-value, and prt for the p-value as well. We use var diff to make sure that all of those values are in respects to the difference between the two groups. And then when we go ahead and hit run, we can see a table with all of the statistics that we had asked for. Most notably, we can see that we have a really low p-value of 0.0059. And with such a low p-value, or comparatively lower than a significance level of, say, 0.05, we can conclude that the two groups do in fact differ in mean value. That is to say that we reject the null hypothesis where the two groups means are the same or the difference is equal to 0, and conclude that in fact the difference is not equal to 0 between the two groups. And before we move on to the third question, I'm just going to go over proc t-test for this example, where it's a bit more thorough than proc means. So if we use that proc t-test function, and then with our data, and then with the option paired with our variables initial and final separated by an asterisk, we can go ahead and run that. We get a similar output as the last example. And then if we scroll down here to the very bottom of the output, we can see that there's going to be a QQ plot. Along the way, there's also a number of different and helpful diagnostic plots as well. And again, judging by the QQ plot, the data here does in fact look normal, as the residuals do trend linearly along that line there as well. And then just like the proc means test that we had performed earlier, we can see that the p-value here in table 3, we can see that the p-value is 0.0059. So again, we can make the same conclusion that the two groups do differ in means. And just one last note here is that the added benefit of using the proc t-test over the means is that you get the same summary with the addition of the confidence intervals for your estimates as well. So heading over to our third question now. So for this next problem, we're going to be figuring out the sample size necessary in order to meet these criteria as displayed in this question here. So first, we notice that we're going to be testing at a 5% significance level. Reading on, we have a two-tailed hypothesis test where mu1 minus mu2 is equal to 0, and the alternative is that the difference does not equal 0. Next, we see that the mean of group 1 is 0.8. And it asks us to determine the number of subjects required to ensure that the probability of detecting a difference of 0.4, for example, when mu1 minus mu2 is equal to 0.4, when mu2 is equal to 0.4, or in the scenario where mu1 minus mu2 is equal to 0.3, when mu2 is equal to 0.5, with 80% power. It also asks to conduct those same tests with 90% power in mind. And then finally, we see that the variance is equal to 0.3. So taking that all into consideration, I made this table here for the 4 different scenarios. So as you can see, alpha, mu1, and sigma remain static, where power and mu2 are variable. It had asked to assess the sample size for power at both 80% and 90%, hence the 2 values in the power column. It then asked to assess when mu2 is equal to 0.4 and 0.5. Thus, we have 4 different possibilities. And to find the sample size for a two-sample, two-sided test, we can follow this table. So here at the very bottom, and then to the right, we have this formula for the sample size. So we're actually just going to apply that formula in SAS, and we're going to print the results. So as always, we're going to start off by creating a data set. Then we're going to input variables alpha, power, mu1, mu2, and sigma, as described in the problem. So this line creates a variable in which finds the z value that has area to the left 1 minus alpha over 2 under a standard normal distribution. In this line, we create variable beta that is simply 1 minus the power. So this line, similar to the third line, is a new variable in which finds the z value that has area to the left 1 minus beta under the standard normal distribution. So this line creates a new variable for our effect size, which is simply just the absolute value of the difference between mu1 and mu2 divided by the standard deviation. So this line creates a new variable that adds the 2 z values found, divides it by the effect size, then squares that result, and then multiplies it by 2. And because we want a nice round number, we take the ceiling function, or rather, we just round up that temp2 to find our sample size. We can actually use the data lines and then import that table that we had created earlier to apply all of those variables to the different scenarios. And so when we run it, we'll be able to find the sample size for each of those different scenarios. So here we can see with all of the different variables present, and the last variable should be our sample size. And just for a more aesthetic output, we can use the proc print function. And because we don't need all of the variables that were temporary, we can use var alpha, beta, mu1 and mu2, sigma, power, our effect size, and our sample size. So we can go ahead and run that. And so all those values found in the N2 column, those are all the sample sizes necessary that coincide with the different scenarios set in place by the problem. And as you can see, the sample size is not static, and it depends on factors like the mean and the power of the scenario. So yeah, we can take that knowledge and we can actually do the reverse. So for this next question, we're going to find the power given the sample sizes that we just found. So here's the table that we're going to be using. Here you can see that we've replaced power with the sample sizes that we had just found in the last example. So again, we're going to start off by making a new data set, this time with variables alpha, n, mu1, mu2, and sigma. Again, we're going to find that z value and save it as a variable. So it's going to be the z value with area to the left, 1 minus alpha over 2. So like last time, we're going to create the effect size variable, which is the absolute value of the difference between mu1 and mu2, divided again by sigma. So this line creates our last variable power, which is 1 minus the area to the left of a normal distribution of the value z underscore alpha 2 that we had created minus a fraction of the effect size over the square root of 2 over n, and then we specify the standard normal with 0 and 1. So then we can input the table featuring the sample sizes that we found in the last question. So we can go ahead and run that and create the data set. Looking through the data set, looks like everything was imported properly. So we can go ahead and use a proc print function so we can get a more visually pleasing table. So we're just going to use the necessary variables this time. We're going to exclude some of the temporary variables. So if we go ahead and run it, we can see the table. And if we look at that last column, we can see that the powers perfectly replicate the powers input in our last question. So everything seems to have checked out. Alright, so that actually concludes our tutorial for today. So if you have any questions, feel free to stop by office hours and I can help you out. Alright, thank you.